And now comes the non-trivial part, the essential part. The essential part is the idea of approximating that, because we haven't done anything yet toward the computation. We still don't know how to compute any of those areas. What we do now is the approximation. So we approximate each of those tall pieces by a rectangle. It seems like a rectangle, although it is not, because the top part is curved. So approximation of AI by a rectangle. So that's the geometric idea, and the idea is to approximate it by something that we know exactly how to compute the area of. Okay? So it's the idea of reduction of something difficult to something simple. And once you reduce it to a rectangle, well, rectangle has the area equal to width times height. Okay. Put it as height times width. Height with index I, because we are talking about ith rectangle, and times width with index I, because we're again talking about ith rectangle. Now the typical assumption at this point is that when we subdivide into those vertical columns, we subdivide into columns of equal width. So it is just assumption to simplify matters and to have only one simple notation for that width. It is denoted by delta x, and we know exactly what it is. Right? It's the length of the whole interval, which is b minus a, divided by the number of pieces. Right? But as soon as we assume that all the widths are the same, that's exactly the width of each piece. So we will keep this notation delta x, and for the height, the value is, well, it's not that easy to determine. The height of this thing is going to be the height of rectangle, but which rectangle to choose, right? So sometimes the graph is almost horizontal, so it is almost obvious that it's this rectangle, but sometimes the graph is increasing rapidly, and then you can choose one rectangle or the other, and the heights are going to be different. So at this point we really do the approximation. Right? The approximation is going to be either by the value of the function at left hand point. So if this is ith interval, then the rectangle I choose right now is rectangle having height equal to the value of f at this endpoint. So it is f of left endpoint, and again I put I there because it's left point of ith interval. Or we can approximate it by the value of f at the midpoint. It would be something like this. In this case, a taller rectangle. Or we can choose right hand point, or we can choose some point. It will still be an approximation. And the reason I'm listing all these three is because those are the standard things commonly used. So that's the only reason. Otherwise, you can choose some point, and that introduces some randomness in this choice. You can possibly choose left points for every odd interval, right points for every even interval. whatever you can imagine, just choose some point. But that kind of randomized procedure is more difficult to implement in computation, for example. If you want to write a program to compute something, you would like some order, you would like some precision. So you choose either left point or midpoint or right point. Alright, and then, so what do you do with that approximation? Well, then you say that the area which is exactly equal to the sum of areas AI is approximately equal to the sum of those products. So let me write those approximations in each case. So the area is approximately equal to this so-called Ln, the sum from 1 to n of f of left point with index I times delta x. It is also approximately equal to mn, which is just a notation for summation of the values of the function at the midpoint. Delta x, or Rm, the similar thing when you add up values at the right points. Or in general, you may think of sum of values at some point. We call it xi times delta x, where xi belongs to ith interval. Alright, now we come to the point where the area is approximately equal to something.